Assalamu alaikum everyone. So today we're gonna solve some problems from the gear. And the book will be following today's the Walden book, okay, second edition, and chapter 12. Okay, the book is uploaded in the Google Classroom along with the solution manual. So the first problem that we're gonna solve today is from the exercise chapter 12, exercise number 10. So the first thing that you need to do that this kind of gear train is given, that you have to identify that what kind of gear train is this. So as you can see, this is the gear number 2 and this is the gear number 5. So as you can see that the gear number 2 and 5 are coaxial. Their axis of rotations are coaxial. Okay, so that means this is what? A reverted gear train. Now, what is said in the question that gear reduces to be designed. This is a design problem. In the figure, they determine the diametral pitch and the number of teeth on the gear 4 and 5. And they have given the gear 2 speed is 10 times than the speed of the gear 5. And the pitches of the two gears, one of the conditions is given is that the pitches of the two gears should be as equal as possible, nearly as equal as possible. That means that the diametral pitch that you choose during the design, that should be closer to each other. Okay, and another condition is given is that no gear should have teeth number less than 15. Okay, so how to proceed with this kind of problem? First of all, we're given omega 2 is basically 10 times the speed of omega 5, so I can write omega 2 by omega 5, which is basically 10. And that is basically the velocity ratio. That means the input divided by output. Now, if the velocity ratio is like that, then you need to see that if you want to represent this in terms of the teeth number, and as we know that the teeth number are inversely proportional to the angular velocity. So to determine in terms of the teeth number, you have to see that how the gears are meshed. Okay, so first of all, you have to see that we have to go from 2 to 5. And it has two stages. In the first stages, the gear 2 is rotating the gear 3. So 2 is rotating gear 3. So it should be what? As the gear teeth are inversely proportional, it should be N3 by N2. And there should be a negative sign. Why there is a negative sign? Because you know that if one gear rotates, let's say clockwise, then the other gear is going to rotate anti-clockwise. To keep track of the direction, this negative sign is taken. Okay? And if you have this kind of gear phenomena, like one gear rotates clockwise and another gear rotates anti-clockwise, then you have to use this negative sign. Okay, now we are on the gear number 3 and 3 rotates 4 at the same speed, and then 4 is going to mesh with the gear number 5. 4 is meshed with the gear number 5. So you have to write, and here the same analogy. If one rotates clockwise, then other is going to rotate anti-clockwise. So you have to write N5 by N4, basically 10. Okay, from this equation, the N3 is given as 30, N2 is given as 20. So if I input these values, you're going to get N5 by N4 is basically 20 by 3. Okay, this is the equation number 1. Okay. One of the important conditions during our discussion about the reverted gear train was like that. If this is the reverted gear train, and if this is the R2, and this is R3, if this is R4, and if this is R5, then one of the important conditions of the reverted gear train was like that. R2 plus R3 is basically R4 plus R5. Okay, and if I want to write this equation in terms of the diameter, you have to multiply this equation by 2. Okay, then you can write this in terms of the diameter. We're going to get D2 plus D3 is basically D4 plus D5. Okay, and as I said during the last lecture, that if one gear is going to mesh with another gear 2 and 3, the diametral pitch should be equal. Okay, so that means in the first case, if I want to show you that, in the first case, the gear 2 is meshing with the gear 3. So their diameter pitch should be equal. So that means P2 should be equal to P3. And in the second case, the P4 is matching with the P5. That means their diameter pitch should be equal. So that means P4 should be equal to P5. Okay, so what is diametral pitch? Diametral pitch is basically N by D, and if I want to write in terms of D, it should be N by P. And if I want to put in this equation, we're gonna get what? D2 I can write in terms of N2 by P2 plus D3 N3 by P3, but as P3 and P2 are equal, we're going to write P2 directly. And similarly, on the right hand side, we're going to have N4 by P4 and plus N5 by P4, as P4 and P5 are equal. So from this equation, I can write N2 plus N3 by P2 is basically N4 plus N5 by P4. Okay, the N2 value is given as 20, N3 value is given as 30. So if I input these values, we're going to end up with, and we're given an N5 by N4. This ratio is given. So now if I write P4 by P5 times 50 is basically, if I take common N4 from this side, we're going to end up with 1 plus N5 by N4. Okay, so now if I want to write all in terms of N4, we're going to end up with, and this ratio is given as what? 20 by 3. Okay, if I input these values, we're going to end up with N4 is basically 150 by 23 times P4 by P2. This is the equation number 2. Okay, you have to use these two equations to iterate, to determine the diameter of pitches and the teeth number. But the conditions is that that means the teeth number, that means the N4 and N4 must be integer, as there cannot be a fraction number of teeth number. Okay, there should be a total number that should be integer. That is one of the conditions. And another condition is that the diametral pitch you choose, they should be closer to each other. That means we have to choose the P2 and P4. P2 and P4 will be closer to each other. We have to choose in such a way that they should be closer to each other, as nearly closer as possible. Okay, now we have to iterate. We have to iterate by this table. This table is given 7.1. In this table, the standard diametral pitches are given, and also the module. Okay, but if you see in the solution manual, they have used more values than the values are given in this table. Okay, that is also true, because there is another table in the machine design book where more values of the standard diametral pitches of the gears are given. Okay, they have used that one. Okay, but if you're asked to solve this kind of questions and you are given this table with the question, then you have to choose the value from this table and iterate. Okay, and this is a design problem, so there is no fixed solution. You have to show maybe 3 and 4 iterations, 5 iterations, 3, 4, 5 iterations, and that would be enough. Okay, and you have to choose from this table if this table is given. Okay, so first of all, how do you iterate? We have to choose. Okay, so first of all, in the first column there should be P2, and second column P4, and the third column there should be N4 and N5. Okay, so you have to choose from this table. Okay, so if I choose P2 as 1.75 and P4 as 4, we're going to end up with N4 as closer to 15. Okay, or we have to approximate to 15, and N5 should be, if N5 4 is 15, from this equation, the equation number 1, we can determine the value of N5. N5 should be what? N5 should be 100. Okay, now if I choose for the second iteration, if I choose the P2 as 12 and P4 as 44, then what should be N4 from equation 2? From this equation, it should be 150 divided by 23 times P4 is taken as what? P4 is taken as 44, and P2 is taken as 12. So it will end up with 23.91. Sorry, we're getting 23.91. We have to approximate that to 24 number of teeth. If the N4 is 24, then from equation 1 we can determine the value of N5. 20 by 3 and times 24. You're going to end up with 160. Okay, so you have to do the iteration in such a way that, and remember, you have to choose the diameter bit in such a way that you get the value of n4 and n5 in terms of an integer number, because there cannot be a fraction number of geared teeth. Okay, so you need to show some iterations, and that is it. Okay, that is how you need to approach this kind of designing problem. And as I said, there is no particular solution for this. This is a designing problem. You can have more than one solutions. Okay, all of them are correct. Okay, all of them are correct. Okay, now we're gonna move forward to the planetary gear train. So in the planetary gear train, I think I have discussed during our first lecture on the gear that in the planetary gear train we'll have one sun gear, and the sun gear there will be more than one planet gear. These are planet gears. Okay, these are called planet gears, and this is called the sun gear. And the sun gear and the planet gear will be connected by a carrier. Okay, this bar is called, this arm is called the carrier. Okay, and this whole thing is going to rotate in an internal gear, in an internal casing, that is called the ring gear. Okay, that will have an internal engagement, okay, with the planet gear, and the planet gear is going to rotate along this ring gear. So that is the basic of a planetary gear train, and I think we have discussed during our first lecture about the planetary gear train. So now we'll move forward to solve some problems from the planetary gear train. Okay, so the first problem that we're going to solve is from the Waldron book, the example 12.4. Okay, so this is your problem. This is a planetary gear train, and in this question you are given as omega c, the carrier velocity is given as 150 rpm, and that is in clockwise direction, and also the omega 5 is given as 50 rpm, and that is also in the clockwise direction. Okay, so as I said that when you see that we have determined the angular velocity in terms of the teeth ratio, then we have taken a negative sign. If one gear rotates clockwise and then another gear rotates clockwise, if that is a phenomenon, we have taken that negative sign. So that negative sign is to keep track of the rotation of the gears. Okay, so if you take, okay, for the reference, if you take counterclockwise as positive and clockwise as negative, then this omega c is a clockwise, that should be negative, and this omega 5 as clockwise, that is also should be negative. Clear? Okay, so now how would you proceed with this kind of problem? So if you are given this kind of problem in terms of the planetary gear train, you have to use the relative speed in terms of the carrier. Okay, so you know the definition or the concept of the relative velocity. I think we have also discussed in the velocity analysis chapter. So the concept of the relative velocity is like that. If I want to, as I said, that you need to represent the velocities, the angular velocities, the relative angular velocities in terms of with respect to the carrier. Okay, let's say the relative speed. Okay, the relative speed. If I want to represent or determine the relative speed omega 2, okay, in terms of the carrier, so how can I write? You have to write that particular speed omega 2, and you have to subtract the speed that we're taking reference to. That means we're taking reference in terms of which speed? The carrier speed. So you have to always subtract that one that you take reference to. Okay, that should be omega c. Okay, that is it. And now if I want to write what is given, omega 5 is given. Okay, so if I want to write the omega 5 in terms of the carrier, I can write c omega 5 is basically the omega 5 minus omega c. Okay, c omega 5 omega c. Now what can you do? Okay, you know, this is our input gear. The gear number 2 is input, and our output gear is the gear number 5. So if I want to write in terms of the velocity ratio, how can I write? Okay, I can write the velocity ratio. That means c omega 2 input velocity divided by c omega 5. Okay, c omega 2 divided by c omega 5. This is the velocity ratio. And how can I write? Now if I want to write in terms of what? In terms of teeth number, I have to see that how the gears are meshed. So we have to go from 2 to 5. Okay, so the two stages. First stage is what? Not actually, basically there will be two ways to go. First of all, 2 is meshing with the gear 3. Okay, 2 is meshing with gear 3. So how can I write? I can write n3 by n2, and there should be a negative sign. Why the negative sign? But if gear 2 rotates clockwise, then the gear 3 is going to rotate anti-clockwise. To keep in the direction, I have written this negative sign. And then the 4 is meshing with gear number 5. So I can write n5 divided by n4. There should be also a negative sign. So negative cancels out, it becomes positive. Okay. Now if I want to write the teeth number given, n3 is given as 30, n2 is given as 18, and then n5 is given as 20, n4 is given as what? 28. We're going to end up with 1.1905. That is basically the velocity ratio. Okay, that is basically the velocity ratio. Okay, we have determined the velocity ratio. Now we have this equation. Okay, so c omega 2 divided by c omega 5 is basically 1.1905. Okay, now if I replace this c omega 2 in terms of this relative velocities, that means I can write c omega 2 as omega 2 minus omega c, and omega 5 I can write in terms of omega 5 I can write in terms of omega 5 minus omega c, and that is basically 1.1905. Okay, what is the value of omega 2? You're asked to determine the value of, I think, omega 2. Okay, you're asked to determine the value of omega 2. So I have to write omega 2 as variable. What is the value of omega 6? Omega 6 we have taken as reference. Omega 6 is minus 150, negative 150. So it should be plus 150, because as a reference we have taken anti-clockwise positive and clockwise negative. Okay, based on that we are given the sign here. Okay, and what is the value of omega 5? Omega 5 is given as 50 rpm, minus 50 minus what is the value of omega c, plus 150, 1.1905. So from this equation, if you get the value of omega 2, you're going to get the value of omega 2 as minus 30.95 rpm. Okay, that means what should be its direction? We get negative sign, then it should be clockwise direction. Clear? So that is how you need to solve the problems for the planetary gear train. Okay, now the next problem we're going to solve is from example 12.5. This is also from the Waldron book. Okay, this is also a planetary gear train, and in this question what you were asked that the driven gear, the tilt is driven at speed 60 rpm in the counterclockwise direction viewed from the right end. This is your right end. If you see from here, you're gonna see that it rotates counterclockwise. Okay, so the gear 4 meshes with a fixed ring gear. The ring gear is fixed, and with gear 5 as shown. Find the magnitude and direction of the angular velocity of the 5. You are asked to determine what omega 5 is what. Okay, and omega 2 is given as 60 rpm counterclockwise. As counterclockwise is given, we're taking counterclockwise as positive, so the value is positive. Okay, so now how can you determine? Okay, So, as I said that if the planetary gear problems are given, you have to always represent the velocities, relative velocity with respect to the carrier. Okay, here this is the carrier. Okay, so you're asked to determine omega 5 and omega 2 is given. So you have to write C omega 2. What should be what? Omega 2 minus omega C. And then omega 5, C omega 5 should be what? Omega 5 minus omega C. Clear? And then what? The gear number 7. Okay? Gear number 7. Gear number 7 is the ring gear. Okay? Gear number 7 is the ring gear. Okay, this is the gear number 7. Okay, this is the ring gear. This is the internal ring along with the planet gears will rotate. That means the gear number 4 is going to rotate. Okay, so the gear 7 is basically the ring gear. So there is a one advantage that if you represent like the C omega 7 minus omega C. Okay, one of the advantages is that the ring gear is stationary. You know, it's actually clearly written I think in this question with a fixed ring gear. Okay, the ring gear is fixed. That means what? That means the ring gear velocity, that means omega 7 should be 0. The ring gear is not going to rotate. It is an internal gear, so it cannot rotate by itself. You remember the example of the rack and pinion. The rack cannot rotate. Okay, on the rack the pinion can rotate. The similar concept is here, because then the rack will not have any angular velocity. Similar concept is here. The internal gear, the gear number 7, the ring gear, that means it cannot rotate. Okay, that means its angular velocity is 7. So this is one of the advantages, like we are getting out of one. If you represent omega 7, we're getting rid of one of the variables. Okay, so that is one of the advantages to represent a C omega 7 in terms of in the carrier. Okay, so now you have to write in terms of the 7 gear. Okay, you are given what? You are asked to determine you are given this omega 2 velocity. This omega 2 is given, and if I determine this omega 7, okay, then we can if we, okay, what I'm saying is basically C omega 2 by C omega 7. Why is that? Because if you do that, then you see, you know the value of omega 2 and you know the value of omega 7, that is basically 0. So one of the variables cancels out. So then you can from this equation you can determine the value of the carrier, the angular velocity of the carrier. Okay, so if I proceed, you will understand. So C omega 2 by C omega 7, how can I do that? We're going from 2 to 7, so we have to write in terms of what? In terms of teeth number. So first of all, see, 2 is meshing with 3. You have to write what? N3 by N2, and as if one rotates clockwise, then other rotates anti-clockwise, so you should have to use the negative sign. Okay, cross. Then 4 is going to rotate in this ring gear. This gear number 4 is going to, this is a planet gear, is going to rotate in this ring gear. Okay, along this ring gear internally. Okay, so this is, how can I write? N7 divided by N4. But should I have to use the negative sign? No. As I said, if the phenomena is one rotates clockwise and the another rotates anti-clockwise, then only you have to use the negative sign. But if one rotates clockwise or anti-clockwise, doesn't matter, but the other, that means in the internal gear, the ring gear, it is not going to rotate. So you cannot use a negative sign here. Okay, there should be no sign. Clear? So if I input the values, what with the omega 2? Omega 2 minus omega C divided by omega 7 minus omega C is basically N3 value is what? N3 value is negative 30 by N2 value is 18, and into N7 value is what? 76, and what is the N4 value? N4 value is 28. Okay, so now if you solve we have the value of omega 7 as 0, omega 2 as what is positive 60. So if you solve for omega 6, you're going to get the value of omega 6 as positive 10.86 rpm. That means what will be its direction? Counterclockwise. Okay, counterclockwise. Now you're asked to determine what? You're asked to determine the value of omega 5. So you have to use what? C omega 2 divided by C omega 5. That is basically omega 2 minus omega C divided by omega 5 minus omega C. And how the gears are meshing? They're going from 2 to 5. So 2 is meshing with 3. So you have to write what? N3 by N2. There will be a negative sign, the same reason. And then 4 is meshing with the gear number 5. There also be a negative sign, the same reason. Okay, so now you have the value of omega 2, that is what? 60. And omega C is what? Counterclockwise, that should be positive 10.86. 10.86. Maybe you have to determine the value of omega 5. And then what is the value of omega 6? Omega C. Omega C is the carrier angular velocity, that is 10.86. Okay, and from here 30 by 18 times 20 by 28. Okay, 20 by 28. Okay, now if you solve for omega 5, you're going to get the value of omega 5 as 52.1376 rpm. And as a positive, what will be the direction of this? It will be counterclockwise. Clear? So this is how you need to solve this math. Clear? Okay, now we're going to solve another example. That is the example 12.6. This is also from the Waldron book, and this is also a planetary gear train problem. Okay, but this problem a bit complicated compared to the last few. So what is the question stating? It's a two-stage planetary gear train. There will be two stages, and the gear 2 is the input gear. Gear 2 is the input gear, and the carrier is the 7. Okay, the carrier is input, remember, and carrier 7. So sorry, carrier 7. This one is the output. Okay, the carrier 7 is the output, and the gear 4 is a ring gear that is fixed. This is the ring gear that is fixed, and the carrier of the first stage is 6. Okay, and it is rigidly connected to the gear that drives the second stage. Determine the velocity ratio of the drive gear. Okay, so what you are asked to determine, first of all, you need to make sure of that. You are asked to determine the omega 2 by omega 7. That's the velocity ratio. Okay, so how can you proceed with this one? First of all, you have to determine the stages. How many stages are there? As stated, there are 2 stages. So first of all, you have to differentiate the stages. The first stage, for the first stage, you see there will be gear number 2, 3 and 4. 2, 3 and 4. And what will be the carrier? Carrier should be this one. This one is the carrier, and as is stated in the question, the carrier is rigidly fixed to the 6th number of gear. Okay, you know, it's given the member 6 is the carrier, and that is rigidly connected to the gear. So that means this will have the same velocity of the gear 6. Okay, so the carrier is the 6th number of gear. Okay, and the second stage is that in the second stage, if I use a different color, in the second stage we have the gear number 6, gear number 5, gear number 5 and gear number 4, and okay, gear number 6, 4 and 5, and what should be the carrier? Carrier should be the gear number 7. Sorry, not it's not a gear, the carrier should be 7, the member 7. Okay, there should be 2 stages. First of all, the main thing of solving this thing is actually basically you have to determine the stages. You have to know that how the motion is being transferred to the stages. Okay, so first of all, now what you need to do, as the gear 4, the ring gear, that means what would be the angular velocity? Omega 4 should be 0. So yeah, if you determine anything in terms of the ring gear, one of the variables should be cancelled out. So that will be advantageous. Okay, one of the advantages. So first of all, what you need to do then? We are given what? Nothing is given. Okay, only the teeth numbers are given. So let's say start with C omega 2. First stage. Okay, we're considering the first stage. So C omega 2, from 2 we're going 4, C omega 4. Okay, so how the gears are meshed? First of all, the gear number 2 is meshed with the gear number 3, so it should be what? N3 by N2, and as one rotates clockwise, another is going to rotate anti-clockwise, so we have to use the negative sign, and times gear 4, and then gear 3, this gear 3 is going to rotate in this internal gear, the gear number 4. So how can I write that? I can write N4 divided by N3. Okay, and there should be no negative sign because only the gear 3 will be rotating. Okay, so N3 cancels out. So I can write, what will be the C omega 2? I can write 6 omega 2. This is 6. Okay, 6 omega 2. Sorry, this should be 6 omega 2 because the carrier is 6. You have to always represent the relative velocities in terms of the carrier. As in the first stage the carrier is 6, we have to represent the relative velocity in terms of the 6. Okay, so I can write the omega 2 minus omega 6 divided by omega 4 minus omega 6 is basically what is the N4? N4 is giving us 58, and what's N2 is giving it 8, and there should be a negative sign. Okay, now what we know, we know nothing but the omega 4 is 0. So if I want to write this like in terms of minus omega 2 by omega 6 plus 1 is equal to minus 58 by 8. So now if I write omega 2 by omega 6 is basically 1 plus 58 by 8. Okay, and then if I write omega 6 is basically omega 2 divided by 1 plus 58 by 8. Okay, this is one of the equations. Okay, now we'll move forward to the second stage. Okay, in the second stage, what is going on? In the second stage, the carrier is the arm 7. Okay, the carrier is the 7, the member 7. So you have to represent the relative velocities in terms of the 7, the member 7. So what we have, how the motions are transferring, 6 to 5, and 5 is rotating on 4. Okay, so I can write 7 omega 6 divided by 7 omega 4. Why omega 4 we're taking? Because if we take omega 4, then omega 4 velocity is known is 0, so one of the variables will cancel out. Okay, that is actually advantage. That's why we're going from here. And if you also see in the diagram, 6 is rotating the 6 is rotating the 5, and 5 is rotating on the internal gear 4. Okay, 5 is the planet gear, and that is rotating on the ring gear, that is 4. Okay, now how the velocities the gears are meshed. So it is meshed, you see, from 6 to 5. Okay, 6 is rotating 5, so what it would be, n5 divided by n6, and it should be a negative sign, same reason. Okay, and then 5 is rotating on 4, there should be no negative sign. 5 is rotating on 4, so it should be what, 5 is rotating on 4, so it should be n4 divided by n5. Okay, so no negative side. So if you input the values, what it should be, omega 6 minus omega 7 divided by omega 4 minus omega 7. And what is the n5? N5 cancels out. It should be again minus 58 by 8. Okay, now if I again write omega 4 is 0, omega 6 by omega 7 plus 1 is basically minus 58 by 8. And if I do the rearrangement, we're going to get omega 6 by 7 is basically 1 plus 58 by 8. From this equation, if you write omega 6, it should be omega 7 times 1 plus 58 by 8. What is the value of omega 6? From this equation, the equation number 1, I can write omega 2 divided by 1 plus 58 by 8. Okay, and that is basically omega 7 1 plus 58 by 8. And what you are asked to determine, you determine omega 2 by omega 7. So I can write and rearrange. Omega 2 by 7 is basically 1 plus 58 by 8 square. So you're going to end up with the velocity ratio as 68.0625. Okay, that is the answer. Okay, so that is how you need to solve this kind of problem if the planetary gears have more than one stage. Okay, then you have to approach in this manner.